Okay, I think we'll go ahead and get started. Let me go ahead and open up in prayer, and I'll give you some context for what we're going to be covering today, as well as the next handful of lectures. Um, so, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course, Lord. I pray that the material will be clear, that they all can understand what it means to be an engineer, and for this course, what it means to be a systems engineer and what it would be like in the day of the life of in being in that profession. Help them as they're all getting close to getting to the transition of finishing up their time at APU and landing the job that they would like to have in the future. Pray you'd also help them with their spiritual formation, Lord, that all of the times that they're studying scripture, that they can take it to heart to really understand at a deeper level the message of scripture and how over so many thousands of years, the writers have put together an amazing complement of things that God wanted us to know about. Help them to become proficient in the theological methods, how we can take that information and apply it to our day-to-day life, and give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Well, we're coming close to the end of the course relative to the beginning. And so I'm going to just have a little bit of a review of some of the stuff from our main textbook, but mostly focus on some other related material that will help us to get a little bit deeper to be thinking about SysML, model-based system engineering, and maybe helping you to think how you're going to finish up with your final project report and presentation, and give you some resources that maybe would help you to go to that next level. So we got our main textbook, which we're quite familiar with. We literally went through it chapter by chapter, and it's the best one that I found in terms of giving you a nice overview of what system engineering is. We have our practical guide to SysML. And so I hope that you found this was a benefit as you're doing your modeling, to give you some examples. And I've highlighted some stuff in there. There's actually a really good appendix that will show you some of the syntax, some of what we did, but there's a lot of things that we haven't bumped into. There's really no way I can show you everything that's within the SysML standard. But I tried to give you a nice context in relationship with what you're doing with your project. I've also had a space theme, and so NASA is a good way to be thinking about it. You've seen how I've talked a lot about the James Webb Space Telescope. I've also talked about a couple other threads as a way to give you some context, because when you're applying system engineering, model-based system engineering, and using tools like SysML, having a context is really what it's all about for systems engineers. So we really went through the whole life cycle of what a system engineer does. We gave some general principles, and spent some time to give a way to be thinking about going through the system engineering V. And the big place where it's pay dirt for system engineers is really in this front end. So we had a whole lot of chapters that were talking about all of these things. You have to envision what you want. Requirements are huge, hugely important. And then when you get an idea, then you start to have to do some analysis and slowly refine it to a point where it's ready to actually go into development. And so then at that level, it's about on par with the subject matter experts in particular fields, and the system engineer is playing the conductor, trying to wire all these things together, glue it together, make sure it's all appropriate. And then finally, once you've gotten that development, then you get into the operation, which they call post-development. And so it's actually in its operational environment that it's meant to do, and it's going through that full life cycle. So you have to be thinking of operations and maintenance. And then we started to talk a little bit higher about enterprise, that you can have systems of systems engineering. We talked about security issues, and we talked about the future of system engineering. And one of the things that I have been doing is applying system engineering principles towards biological systems. At the very beginning of the class, I mentioned that and recently got an article published in a system engineering journal applying that. And I'll come back to that a little bit, but not a lot of details. So we've been talking about the James Webb Space Telescope as well as CubeSats as sort of representatives as one way to be thinking about it. And so these were some charts that I put in that I haven't shown you yet, but just a few more charts about the James Webb Space Telescope. And so here we can see where it's in its orbital regime. And so there's the sun and there's the Earth. And so this L2 point is with the gravitational pull of each one of those things that keeps it stable in that one place. And so a better rendition with this would be the all of these solar shades should be in the direction of the sun, but for representation, it's nicer to see it like this, but that would be a different orientation when it's actually in an operational mode. So it does a couple of things. It's really good at taking images, but it also do spectrographical analysis. And I'll show a chart of what that was like. And so here are the different types of instruments that they have. And so you have this really pristine platform to have the telescope, and then behind the telescope, all of these different instruments that you can have it do one or multiple ones that are activated for a particular event. You have to schedule time. And so all of that needs to be conducted. That needs to be passed to the James Webb Space Telescope for that all to happen. So you have the near infrared spectrograph. And so that's this one over here. You have the fine guidance sensor / near infrared stillness I'll just call it spectrograph, sorry. And so this is like you can see all of this spectral type of things that they have. And then we have the near infrared camera. So you have cameras down here, and then you have the mid infrared instrument. And so near IR doesn't really need that much cooling, but mid IR, this is something that you really need to be cooling down your platform. And this would be one of the drivers why you have this complicated sun shield, and they also have cryogenics to make it perform well. Then we have the optical telescope itself, and this is actually annotated where you can actually actuate these mirrors to make sure they're exactly within like millimeters of alignment with one another. And so there's actuators behind it to facilitate making that all happen. And so this is just a picture of showing you the cold side. And so the cold side would be that on top here where the actual telescope is. The warm side would be on the bottom, or the hot side. And so this is where the temperature is going to be a lot greater. And there's a huge difference in temperatures between that because of this very complicated sunshade. Just to give you an idea of what the James Webb Space Telescope detects. And so you're looking far away and you're trying to detect a star or maybe an exoplanet. And so you have whatever it's being illuminated by. And so say it's relatively close. So in our solar system, it's illuminated by our sun. And so you can see where are these spectral lines that you would get. And so this can tell you about the composition that is seen there. And so say like we're focusing on something that's transitioning across the sun, you can actually get some perspective on how large that object is, just from the temporal response, how this might be changing in a couple of different ways. So those are just some thoughts, some takeaway thoughts, thinking of it from a slightly different perspective than what we've covered already. Here's an example of a 1U CubeSat. I think some of you, if not all of you, have been to our CubeSat lab, and this is exactly the size of what it would be like. This is one of the centers. It's actually in Northern California, the Ames Research Center. And they have been one of the folks that have been leaning heavily into CubeSat technology. And of course, APU, we're also trying to partner and just started getting our technology and things that we would be doing done as we progress. And so these are just a couple other charts just to give you an idea. I'm sure with your physics classes, you're familiar with degrees Kelvin. And so this is like 0 degrees Kelvin is absolute zero. So we're seeing that, relatively speaking, that's a lot closer than the hot side. So this is like room temperature for what we would be having here sitting in this room. So that's a huge differential between each side of what we have. And this is just another thing. I don't know if anybody saw the eclipse yesterday, but I actually pulled out one of our telescopes, and it actually has this kind of a mirror configuration where you have a large primary, then you have a secondary mirror, and then for us, that's all it has. Here you have tertiary and multiple mirrors that actually can be steering that information to one or possibly more of these instruments at a time through all of these complicated mirrors that direct where the culminated set of information they got that's set by this large mirror to begin with. So those are just a couple thoughts. We are reviewed again what we've covered. We talked a little bit about the James Webb Space Telescope, and now I'm going to flip over to one of the other presentations that I'll be focusing on for some of these future lectures. So the first one that I'm going to use is this one. And so there's actually a couple of tools that we are leveraging in our class. And just to give you an idea, if I just go to, I'm not going to pull them up today, but there is this, I've always used this term Cameo Systems Modeler. And so I have a couple of viewers here, the 2019 version and the 2021 version. And then we have the one that I actually have a license is the Magic Systems of Systems Architect. And so those are some related products that are there. And so when I get into some specific tools, I have a couple charts in this slide deck that will be talking about that. There's also another thing that I briefly wanted to just show you. So there's something called a Hohmann maneuver. And so what it does, it's the optimal way of going from one orbit to another, and you do actually 2 burns. And so this is a tool out there that helps you to be visualizing what's going on in space for missions. And I'm just going to go ahead and play this. And what it's going to do, it's going to show 2 Hohmann transfers, one going from A1, so this lower orbit, so you could think of a low Earth orbit, to something here, a geosynchronous orbit. And so that would be called orbital raising. And it's also going to be showing you a D orbit, so you would be going from A2 down to this low Earth orbit. And so it's not very long, but I'll just play this scenario just to let you see what that would look like. So when you get the first burn, you saw that. So it did a delta V at this point, and now it's in this highly elliptical orbit. So that would be the first of 2 delta Vs that would take place. And the second one, I know it's really faint, but you can see a light outline of now this other orbit here. And so with that second orbital raising, it's circularized that orbit, and now it's in that geosynchronous, geostationary orbit. So for this one, what it's also showing is an example of doing a D orbit. And so we actually have 2 delta V's that actually happen to put it into that orbit. So the first thing you had an orbital raising. So here, it's basically a delta V that's going in this direction. So it's shooting this, and so it's injecting that into making it more. It's going to give this highly elliptical. Then another one here, and that's going to have a delta V going in this downward direction, circularizing it. Similarly, what we would have if we're trying to make it go lower, we're going to make it go slower. So you're going to have a delta V going down in this direction. So it's slowing it there. And then you're going to have this orbit here that is going to be circularizing it to for the fourth and final maneuver. So you're not going to go this orbital raising and then immediately going on orbital deorbital kind of scenario like that. But since some of what I'm going to show in this presentation talks about that, I figure I'd give you a better way of seeing what that is as an example. So that tool is an example of something that's quite useful for space missions analysis. You guys are all doing different projects on different themes, so it would be something slightly different. But having a visualization can actually be quite helpful. And it's not only just a visualization, as I wasn't highlighting it too much, but you can get some of the analytical information behind it to help you figure out the various scenarios. So this presentation highlights Delegati's book, and so the name of his textbook is called SysML Distilled. And so there's an original link from his material, but I've actually added some more content in here and tried to bring in some more thoughts on it. So first of all, it'd be a little bit of review thinking about model-based system engineering. And then it'll talk about model-based system engineering tools. Cameo Systems Modeler would be an example. NoMagic System of Systems Architect, that would be something else. We're using visual paradigms in this course. So those are just a handful of examples. I've had a couple examples that I've been pulling up with the NoMagic System of Systems Architect. Sometimes you've heard me call that Cameo Systems Modeler. You could actually open up SysML models with both of those tools. And so that's one of the reasons why I kind of go back and forth with those naming conventions. And the name of their tool, their model is that they call DelSat 77. We'll talk about that. Also within the slide deck is a return on investment of why model-based system engineering is actually more cost effective. It actually gives us better return compared to traditional document-based approaches. And so this was using real programs from Lockheed Martin. They don't tell us what those programs are, but it just tries to give you 4 examples, one that's used model-based system engineering to give you a perspective. I also, from the Visual Paradigms website, when I was initially thinking about using that tool, they have actual examples of all 9 SysML diagram types. And so I'll finish up thinking about that. So depending on the time, we may get through all of this material, or it may bleed a little bit into Thursday. So let's first of all thinking about the model-based system engineering, giving it an overview. So some of this may be a review, but maybe giving a context for another individual and how they think about it. So model-based system engineering is a formalized application of modeling to support system requirements, design, analysis, verification, and validation activities beginning in the conceptual design phase and continuing throughout development and the later life cycle phases. So when I was talking about our main textbook, we were touching on all of those as we went through the system engineering V. And so we can see how that starts to play out here. Here are some more thoughts about model-based system engineering. It is not a process. It does not replace our existing process sets. So we'll come back to that. And so model-based system engineering can be adopted by any organization to develop and maintain systems with higher quality and reduced costs while fully complying with existing process sets. So that's why this can actually be a useful class, even if you're not going to go into system engineering. It gives you a way of doing system thinking, of how you can be conceptualizing a problem at a high level and starting to get some kind of a basis to think how you're going to proceed. So Delegati talks about three main pillars. First is the modeling language. And so a language example would be like SysML. That's not the only thing that you could use, but that's one we're focusing on our class. Then we can be focusing on methods. I'll talk about object-oriented system engineering method, but there's other methods too, and that'll be in a chart in just a little bit. And then the specific tools. You've heard me talk about these names: Cameo Systems Modeler, NoMagic Systems of Systems Architect, Visual Paradigms, and there's also something called Modelia, which I'll also mention a little bit here. So the languages, so you can have an architectural framework. That's something that is out there. And so there's something for the DoD, Ministry of Defense. This is where we start to be thinking about international coalitions. And there's also a unified architectural framework that is sort of a new version, thinking with collaboration with international partners. So there's that. That's more of an architectural framework. We're using the SysML, which was derived from the unified modeling language. That's something that's out there. And there's also some other things. I haven't really explored these too much up to this point. There's a modeling analysis of real-time embedded systems, MARTE, and there's also business process modeling notation. And so those are yet some other things that are out there. In terms of methods, this first one, I mentioned this acronym already. It's called Object-Oriented System Engineering Method, OOSM. And what I did for biological systems, since it gets into what I would argue is reverse engineering, so I called it Reverse Engineering Object-Oriented System Engineering Method, or REOSM, for how we can be applying system engineering towards biological systems to make us understand what is actually going on in those systems. JPL has something called the state analysis method, and we have talked about a state machine diagram, so you have a little bit of familiarity with what that would be in terms of a focus. Lockheed Martin has something called a model-based system engineering method. And so there's that, and so there's other things listed here on this chart. And a caveat that might be worthwhile to note is no out-of-the-box method will meet a project's specific needs and goals. So that's another example of system thinking. What do you need in your particular situation? And that is the question as a system engineer that you want to be asking. And so it makes sense to start at a high level and conceptualize the big problem, the big perspective, and then you can drill down as is needed to get more specific, because there's a particular question that's been revealed by thinking of that top level observation. Planning for a model-based project requires a customization of a method. And so what I've mentioned with REOSM would be an example, and you all are applying system engineering perspectives with your project that you're doing for this class. Then we get into some specific tools. This will be something we start here. And so here our example, here we have NoMagic, or sometimes they call it Magic Draw. That was another term. So actually the models that I've imported were actually originally developed as what the authors conveyed in Magic Draw, but it can actually be opened up into other SysML tools. For example, I could open Magic Draw. I haven't tried this on my own, but I've heard I could actually import that into Enterprise Architect. And so some of these things are have some overlap that they're trying to make it so you could definitely import existing models. So each tool complies with the language specifications to varying degrees of fidelity. And we've seen that a little bit with what we're doing, and we'll see that come up on our next slide. Some tools offer greater capabilities than others. So that's going to be why you might choose one tool or another. You've seen a little bit when I've shown you the Cameo Systems Modeler / system NoMagic Systems of Systems Architect. that there's a lot of things that are capable, you're able to do that. So there's a lot of flexibility. That means that there's a larger learning curve to get proficient in that. So there's commercial grade and there's also open source. So here are some examples. And so this is based on a presentation that was a while ago. And so I haven't tracked the how things have gone from one vendor to another. But here was a tool by Visual Paradigms, and maybe now they just started to just call their tool Visual Paradigms, even though it's also the vendor. But that's something that we are use. We have Enterprise Architect, we have Cameo Systems Modeler. So it's by No Magic, and now it's Dassault Systems. And so there is movement in the industry. And the first year I taught this course, I was actually using a tool called Modelio. It's open source. And then they really stopped supporting it. The Mac OS version just stopped working. And it's developed by Modelio Soft. And I recently I checked out their website, and now they do have a version that's available for Windows and also for Linux, and so but not Mac OS. And so it's a lot. The version number is like an order of magnitude. It used to be like version 3.5 something. Now it's version 4 something, or maybe even 5 something. And so it's something I'm going to spend a little bit of time, say over the summer, looking at a little bit more. But that just gives you some context. So those are the 3 pillars: the modeling languages, the methods, and the tools. So we got a chance to be thinking about that a little bit more in detail. So what is the model? How do we think about that? The output of a model-based system engineering activity is a coherent and consistent model of the system. That is a system model that is expressed in a standard modeling language. And so, for example, we could do it in SysML. The system model is a set of elements which represent the system's parts, actors, behaviors, events, requirements, constraints, and test activities. And it's a relationship between those elements, the associations, dependencies, and generalizations, flows, etc. So one view is not the model, and so it is something different than that. So you can do this in Visual Paradigms. You can do it in or No Magic System of Systems Architect, or Cameo Systems Modeler. You can start to be exploring in detail some of the model elements from various points of view. And so this is just one way to be thinking about that. A modeler user can navigate the model to view a specific element and the relationships that it has with other model elements. And so here, this is just trying to highlight that we can be looking at our particular area. And then you can see all these things that are related to that block. And so we've seen block definition diagrams where it shows up in a different way within an actual model view. So let's think of the distinction between a model versus diagrams of the model. If the diagram-based engineering approach, designers create a set of diagrams that serve as views of the system design. These designs are even causally referred to as, quote, models of the system. In the model-based system engineering approach, the system model is itself an engineering artifact that has an existing independent of diagrams that a designer may create to provide views of the model for various stakeholders. So the distinction leads to a fundamental precept of model-based system engineering. A diagram of the model is never the model itself. So the model is all this back-end stuff. And so a particular diagram is only a view, one way of viewing the model itself. So a metaphor that the Delegati brings out is the model is a mountain and a diagram is a picture of the mountain. So maybe you can think of, like, if you're in an airplane taking a picture of a mountain, take a picture of Mount Everest. That's one perspective. Another perspective would be at the foot of the mountain. Another perspective would be you standing on top of the mountain. and each one of those would be a different vantage point. So what's the power of a single model repository? The distinction between the model and diagram is the root of the extraordinary return on investment that the model-based approach offers over the document-based approach. So in the model-based approach, if a requirement changes, the designer goes to a single location, the model repository, to make the necessary changes to an element, and the model tool automatically updates all diagrams where the element appears. There's no opportunity for incorrect data entry. Consistency across all views is ensured. And so you can go to the back end, manipulate a value, and it's going to be ripple across the whole thing. Now, this is where, unfortunately, most of my career has been in this document-based system. And guess what? With this model-based system engineering, you're not going to have to endure that, God willing. So in the document-based approach, the designer has to know a priori which diagrams are impacted by the change and where those diagrams are located. Then they have to obtain each of these sequentially and then manually make the change repeatedly in multiple locations, a process which is time-consuming and error-prone. So thus you can see motivation why using model-based system engineering would be a good idea. Some customers, government agencies are a good example. So whether it's NASA or someone else, are often constrained by legislations or regulation to follow a document-based engineering approach. Documents must be formally reviewed, approved, and then archived. And so guess what? A model-based system engineering approach, you can actually still produce these documents. And so it takes that information and put those in that proper form. So that can be requirement specs, interface definition diagrams, design specs, the engineering analysis, and test case specifications and stuff like that. All of those are things that can be taken care of. You can also do this language transformation. You can go from model to code source. One of the things, maybe some of you guys did some programming in Java. And if you use like the unified modeling language, you can actually create code stubs, and you could go that first step of taking your architecture, you start to formulate it into how you want to do the implementation. And thus you can be using UML. And what they're trying to say, you can also use SysML to be helping out in that process in the actualization of a design. So those are just a couple points I wanted to be pointing out of where model-based system engineering, what we have been using, is actually can be quite helpful. Well, the next few charts are going to be doing an overview of SysML, and we've actually been living it, so we don't necessarily have to go through this as in much detail, but we at least want to be thinking about it and maybe helping you with some takeaways for this. And so SysML is a graphical modeling language. We're now getting a chance to think about it, and the key word is language. And so it has a grammar and vocabulary. And so remember that when you develop those diagrams, there's things you can do and there's things that you can't. And so what that means is trying to enforce the grammar and the vocabulary for each one of those diagram types. The SysML language is, quote, spoken by system engineers to visualize, communicate, and document ideas about a system's requirement, structure, behavior, and constraints. Those are all the things that we've got a chance to be familiar with. So SysML is not a methodology. In Survey of Model-Based System Engineering Methodologies, he defines a methodology as a collection of related processes, methods, and tools. A process defines what tasks must be performed. A method used here as a synonym for procedures specifies how the task should be performed. With that in mind, he repeats, SysML is not a methodology. The language can be used to support many different defined methodologies. One of the courses I teach is software engineering. And what we actually do is we flipped it. And so all of the lecture material is something that's made available to students in the textbook. And we actually do the system engineering in the course. That's one of the reasons why the way that I've done this course has mostly been focusing on the project work. And so now when I'm talking about doing system engineering, it can be a little bit harder, abstract, and you've had some chance to be doing it real time with your projects. So there's a history to SysML. This just gets into that a little bit. Back into 1997, hey, maybe we should take UML and customize it for system engineering. And thus has actually turned into what we now know. It's called SysML. So, so the SysML development team was formed to create the initial draft of the specification. It was adopted in 2006, and it continues to mature as we go. We've had a diagram like this that shows you how the 9 diagrams can be broken up into different categories, and you could be either thinking of them as 3 categories or 4. And so there's the behavior diagrams, the requirement diagram, and the structure diagrams, and sometimes a parametric diagram is actually put over as a 4th one when you're focusing on the constraints. And we saw those terms in just a couple of slides. Either requirement, structure, behavior, and constraints. And so we can see it pictorially starting to show up here, but just giving us a structure. So a requirement diagram is used to display text-based requirements, the relationship between the requirements, the relationship between requirements and other model elements. All those things are available. This is something from Delegati when he gives a short description of each of these 9 diagrams. And so if you guys are focusing on a space system, the SysML distilled is useful, but he also has some other material that isn't just space centric, and it's also helpful to just get you a better idea of what you can do with SysML. So there's a variety of diagrams here. I'm just going to be focusing on a few. And so here we see an example of requirements diagram. And so we see requirements are listed on here. We can see other things that are annotated, test cases. And so that's something that we haven't really explored in what we've developed so far, but that's also something that you can be doing. Here is, at the very beginning, I've showed you this Holman transfer. And so there's a couple of diagrams that reflect that in what I'm showing here. And so these just give you what would be the requirements that would be part of doing that. And so this is a proper way of having it. So requirement is supposed to have a shall statement. It also shows you that the DelSat 77 system requirement specification, has its traceability to emission. And here we have a specific requirement. It has an ID number, and then it has a text. And then there's 2 derived requirements that go to a lower level. And there's also a verification method that's laid out. And here we have a satisfied relationship that is included, and a refined relationship that is included in those requirements. So you can see this is even more complicated than we did in the diagrams that we did, but it just gives you an idea of the realm of what can be done. We talked about package diagrams. So one of the ways that we were doing it is I gave an analogy with a CubeSat that you can be showing what you're going to be putting on each board. And so you're doing a structural way of doing packaging. That's possible. There was also an example that I showed that was trying to give you a perspective on what you could be doing if you wanted to give a perspective on how you're organizing things in your model. And so this is an example that's showing you something a little bit more from that point of view. This is back to the SysML model for DelSat 77 that Delegati uses. And this is, I believe I already showed you this in the tool, but this is just trying to give you a perspective on how they organize their model. And I just mentioned that concept. block definition diagram. And so this is how we're showing the different blocks and the association between them. And so the model element type the diagram frame represents can be any of the following packages: a model library, a view, a block, constraint block. These are all the kind of things that you can be including in that. And so here's an example. This kind of perspective of doing a block definition diagram is what I was recommending. And so you have blocks and blocks that are sub-blocks according to that. And so the way we see with visual paradigms, it would then show that these would be parts of this overall satellite when you have this kind of a diamond relationship between those. Here's just another example I won't go into, but they do have like a hybrid SUV as one of some of these charts. I can make these charts available if folks want. I can just save it as a PDF and put it on Canvas. Here are some other examples of block definition diagrams. And so these are for the Delsat 77 model. And so we see this diamond relationships. And so this is just showing you the parts, each of these things that were here. Now they show in this block and they're showing the details. And here just shows you a couple other types of things that you can be doing with a block definition diagram. And I just had a couple more slides with some examples. These are all within the Delegati model. And so I'm just going to skip over these for now. You can actually put in actors into a block definition diagram. And so this is just trying to show you that's available within the syntax of what you could be doing. So they're meant to, block definition diagrams are meant to communicate structural information. We're familiar with that. And so I won't read this line by line. I'll mention this last one. As stakeholders' requirements evolve over time, one can modify existing providers or add new ones, and with minimal impact on the rest of the system design. And so maybe talking with the customer, they say, no, there's another operator that we want to be highlighting, or we're going to refactor how we're going to break things down at a lower level. Those are all possible. The internal block diagram, this is where we get into more detail. We're familiar with that now. We've talked about that. So here is an example for the hybrid SUV. And then we jump back to now be thinking about how internal block diagram would be useful for this Holman transfer. And this just gets into more specifics for the communication and data handling subsystem. And we're getting into the next level of detail as a result. So the parametric diagram, and so this is used to express one or more constraints. And so that's a big thing. You can have like equations in here, and you can have elements that feed into that. So parametric diagrams support engineering analysis to include performance, reliability, availability, power, mass, and cost. They can also be used to support trade studies of alternative candidate physical architectures. All of those are possible. And so now we can be thinking for this hybrid SUV, the things that would be playing into it. And so here we have an equation. The flow rate is equal to pressure divided by 4 times the injector demand. And so thus we can have inputs and outputs that are annotated in a parametric diagram. Here is another example. This is within the Delegati model. And so this is like how you're going to figure out how much delta V, or what does that actually mean? So if you want to have a certain delta V, you have so much pressure that you can have with your stored tank. And so maybe to get that desired delta V, you're going to have it turn on longer so there's a time of operation of emitting some gas through a thruster to get a certain amount of delta V. And so this would be an example of how that could look like in a diagram for trying to think of the constraints. We've talked a lot about use diagrams, and so I'm just going to highlight one or two points here. And so it's supposed to be a high level. You have an actor and a use case that they act with. So this is a different kind of a tool that it shows a stickman slightly differently, just as an FYI for you. And I'll show you a good case of a use case diagram and a bad case. So this first case is a good case. And so the flight controller executes the Holman transfer. You can see like it's a noun verb. The payload operator points the infrared sensor at target. And it turns out that these things all combine together for sending a command. Those are fine. This is not what you should do. This is like a compound. And so this should be aggregated just as doing the Holman transfer, not having these things. This is something that should be fleshed out in another diagram, like an activity diagram. So that's just another point of fact that would be helpful for you to be thinking about. So I'll skip over this chart, but then going back to the Holman transfer. And so this is one that's captured in the SysML distilled. There's an equivalent version. It's the same one, but this is in Cameo Systems Modeler. I mentioned that I have the viewer for two versions, the 2019 and the 2021 version. And so I'll just go back to this version. And so what I was actually was able to show you was with the right type of modules, you can actually execute this. And so you can be checking out your logic. And so there's a couple different diagram types that I showed you. And so that can actually be helpful. So it can be executed in some of these different types of tools. And so that can be going a little bit further to see if is there an error in your logic, and you can play it out. And if there is, then you can fix it. We talked about sequential diagrams, and I was trying to show behavior with a focus on how the parts of a block interact with one another via operational calls and asynchronous signals. So those are all out there. And sequence diagrams are commonly used as a detailed design tool to precisely specify a behavior as an input to a development stage of the life cycle. So there's a communication between different parties passing information, and there's a timing. This has to go first. And so for a CubeSat example, you have to have a command before you're going to get telemetry coming back. And so that's possible. And here is Delegati talks about it in this textbook. This is the activity diagram, one way of visualizing it. And we can have some layers of things in here within this rather than just having a higher level way. This would be a simpler way, and this is what we did in our class with our sequence diagrams, but you can get more complicated and trying to encapsulate different layers of capability within that sequence diagrams as well. So we have the state machine diagrams, and so you have the various states of how things operate. And so this is the hybrid SUV again, so it's either on or off. And when it's in an on state, you can actually have various modes of operation: idle, accelerating, or braking. And so you can have these type of modes and the transition of going from one to another. This would be something for the DelSat 77 model of the different states that you can be doing. And so this is for the orbit insertion and the on-station performance. And you have some examples of nested types of state machines in this diagram, the way it's listed. Well, let me just go through this next one, and I think I'll not go through as much detail about the visual paradigms charts. So here is an example of the return of investment analysis. And so Delegati was pointing this out, and so this was from Lockheed Martin Aeronautics. I know there's been a lot of acquisitions and divestitures, and so this is when Aeronautics was part of Lockheed Martin. And so they don't mention the names, and they use this term model-based systems development. We typically just use model-based system engineering. And so some of the terminology has been a little bit fluid, but I think it's starting to just be model-based system engineering is what we know now. So I have like about 4 or 5 charts. So this first one is a requirements comparison. The figure compares the number of requirements for these 4 aeronautics program. So the model-based system engineering program has a whole lot more requirements. Well, does that mean it's going to cost more? So you can be thinking about that. Then there's the lines of code. So there's a lot more lines of code that are in this. That would be something that, well, that would probably mean that it's actually going to cost more because there's more man hours needed to do all that coding. But the answer is you're going to see that that's not actually going to be the case. Quality comparison. And so the figure compares the number of defects. Look at this. It's a fraction of what all these other programs in terms of what is the defects and the errors. That's going to save you a lot of money. Remember, what system engineering is trying to do is early on capture all of the issues rather than do it later when you're in production, and that's going to cost big bucks. And so this is just an example where it starts to pay for itself. This shows a comparison for the lines of code. So the first one was for requirements. So we can see that the requirements are greater. This other one, we showed that the lines of code were greater. Yet when we start to look at what actually happens with the implementation, because what you've done with model-based system engineering, it ends up being cheaper. And so for both of those cases, for lines of code, as well as for requirements, it's actually cheaper. So this compares the relative cost of these 4 programs in man hours. This is actual values have been omitted, but it just gives you a relative way of thinking about it. It's expected the total number of man hours for the model-based system engineering product system was greater, but that's not the full story. Let's think about it this perspective. However, when normalized for system size, so this one has greater requirements, greater lines of code because the magnitude is much better. But if we normalize it, we can see that it's actually doing, it's more affordable for all 4 of these programs. And so there's the testing. The testing is minuscule as compared to the others. And then for the software, it's on the same order of magnitude for 3, but much less for one of those cases. So let me pause and see if there's any comments or questions on what I shared on that. This gives you some more insight into the advantage of system engineering. What we've been focusing on more precisely is model-based system engineering. And then these last handful of charts are looking at the 9 diagrams with examples of how things are done with visual paradigms. And basically what visual paradigms does is it uses what are the SysML diagrams that aren't anywhere else. And those are the ones that they actually implement. For other ones are actually UML diagrams. And so they say just use as is. And so you remember how I told you what I typically do is I put the 2 or 3 letter acronym for the type of diagram in the beginning, because they actually don't include them in all of them because they don't actually build them. They actually use it, say, the UML perspective of that. So we're familiar with requirements diagrams. One of the critiques that I would have for this is they don't actually use the word shall. They were, and so that's a no-no for contractual reasons. But it is also just showing you requirements, not showing the relationship between requirements for the most part. That was something that we were trying to give some insight into that happening. There's a block definition diagram. You guys are quite familiar with those. And this just shows you those relationships and how when you put this diamond relationship, it'll show up as a part. And so those are, when you have the solid diamond, that's stuff that we saw. The internal block diagram, it also showed you some nomenclature, and I got this from the appendix of practical SysML. And so this is, they have like this ball and circle. And so what this, an interface is represented by either a ball or socket symbol with the name of the interface floating near it. The ball depicts a provided interface and the socket depicts a required interface. So those are some more details that show up in this example of an internal block diagram. That was one of those things that I had an example for that, but I was avoiding going into that for keeping things simple for a first time look through these things. Parametric diagrams, we just talked about that, and this gives you another example of what that would look like. And so you had the flow rate as the pressure times 4 times the injector demand. And so we saw that from, I believe it was a Delegati picture from his hybrid SUV. So it had some of those kind of ideas. And I think it's hidden by this block. I think this is meant to be Presh for that. Activity diagram, we got a chance to be playing that out. Here's just another example, and you could be reviewing that to see if you were to be doing another activity diagram, whether or not you might enhance it a little bit now that you've figured out a little bit more details. Here we see some examples of 2 different things, and we're seeing the relationships between one another. Unfortunately, the way this is viewed, we're not getting a chance to see those arrows back and forth, but this is something that can be done. We're also not seeing the whole diagram, but just keep that in mind. And we have the state machine diagram. And so we have the start. So it's either on or off. And then we have the terminal state, the one when it's done, then you remove the key, and then we have this subsystem, and it has these multiple states within it. And we also saw another one, it wasn't in Visual Paradigms, but this is a rendering of that hybrid SUV, the way that I was talking about earlier for that diagram. And finally, the use case diagrams are meant to be simple. So the user drives this vehicle, and so that would be an example. And there's different things that are part, you can get into more detail that it includes these things, but it's not a compound way of trying to break out what someone is doing. And finally, there's a packet diagrams. You've got a chance to be playing with those, and this is another way that it could be used to be just trying to show a model, how you're packaging it into various parts of what you have. Any comments or questions on what I covered there? All right, so this is one of the extra things that we'll be thinking about as we go through these last couple of weeks. And I think that's a good breaking point. So I hope you guys have a good rest of your day, and we'll meet again on Thursday.